got your hammer? Yeah, it looks like there's been a geologist here before us.
For over 50 years, we've called the moon a dead rock. But the closer we look, the stranger it gets. From water that vanishes in the heat to craters locked in darkness for over 4 billion years, the moon is hiding bizarre secrets. And deep beneath the surface, a buried metallic mass is bending its gravity. These aren't myths, they're hard data. So what's really going on up there? Tonight we dig into the moon's strangest mysteries. Why the moon still makes no sense. It's been more than half a century since human boots first pressed into the gray dust of the lunar surface. The astronauts of Apollo planted flags, snapped iconic photographs, and packed bags of soil for the scientists waiting back home. Since then, probes, orbiters, and landers from around the world have revisited this same desolate neighbor. They've mapped its craters, measured its gravity, and even slammed into its surface just to see what might fly out. By now, you'd expect the moon to be one of the most predictable objects in the solar system. But strangely enough, it isn't. The closer we look, the weirder it gets. For all its familiarity, the moon refuses to behave the way our textbooks once claimed. Its surface soil, known as regolith, clings like static-charged Velcro, coating astronauts' suits and equipment with a fine, sharp powder that seems almost alive. Its ability to store and release heat is inconsistent, leaving vast stretches either baking in blistering sunlight or colder than anything we've measured in the outer planets. Even its interaction with electricity remains confusing. Dust grains can levitate above the surface, charged by solar radiation in ways that shouldn't be possible without a proper atmosphere. These aren't fringe theories. They're real puzzles that scientists continue to confront. Yet the strangest revelation didn't come from what astronauts saw with their eyes, but from what they carried back in boxes. In carefully labeled containers of lunar soil, instruments registered faint traces of compounds that hinted at water. Not lakes or puddles, just molecules. The numbers were tiny, almost ignorable. So tiny, in fact, that most experts dismiss them as contamination, nothing more than Earth's humidity sneaking into the samples during handling. The official story remained that the moon was bone dry. But that assumption wouldn't hold forever. What followed over the decades was a trail of contradictions, subtle signals, confusing measurements, and discoveries that refused to fit neatly into the old picture. One mission after another piled on evidence that something was happening under the dust, in the shadows, and even on the sunlit plains that no one had expected. The moon, once treated as a static rock circling Earth, had begun to show signs of hidden processes that remain frustratingly out of reach even today. And that's where our story begins. Because the real strangeness isn't in the myths or conspiracy theories people spin about secret bases or glowing cities. The real weirdness is in the cold, hard data, the kind that forces scientists to rewrite what they thought they knew. And as we dig into the history of those signals, experiments, and modern missions, the moon reveals itself as something far less simple than a barren sphere of dust. It's dynamic, puzzling, and full of mysteries still waiting to be solved. The secrets of permanently shadowed craters. If you were to stand at the rim of a polar crater on the moon, you'd notice something uncanny. Not the rugged slopes, but the absence of light itself. Down inside certain craters, the shadows are absolute. No dawn ever sweeps across their walls. These are the moon's permanently shadowed regions, or PSRs, and they are among the most extreme environments anywhere in the solar system. The reason is geometry. Earth tilts about 23.5 degrees on its axis, which is why we get seasons. The moon, by contrast, is almost upright, tilting just 1.5 degrees. That tiny lean means the poles never tip far enough toward the sun to let light slip into their deepest craters. As a result, some pockets have remained in darkness since the moon itself formed over 4 billion years ago. The conditions in these shadows defy intuition. Without sunlight, there's no heat. And without heat, the temperatures plunged to extraordinary lows. Measurements from orbit have shown floors inside PSRs reaching nearly minus 400 degrees Fahrenheit. That's colder than Pluto, colder than the surface of Neptune's moon Triton, colder than anywhere measured in the outer solar system. In these pits of permanent night, time itself seems frozen. What makes this so fascinating is the possibility of preservation. If a comet carrying water ice ever slammed into the moon, and we know they have countless times, its debris could have drifted into these shadowed basins. With no sunlight to sublimate it away, the ice could remain locked there indefinitely. In theory, it could survive for billions of years, untouched, a natural archive of the solar system's history. By the 1990s, scientists began to wonder if these cold traps might be more than geological curiosities. If water ice really was tucked away inside them, the moon wasn't just a dead rock, it was a reservoir. Suddenly, PSRs weren't just dark holes, they became potential resources. Ice could be melted for drinking water, broken apart into oxygen for breathing, or even split into hydrogen and oxygen for rocket fuel. The moon could, in essence, become a refueling station in space. But there was a problem. How do you study places that never see light? Sending orbiters to scan from above was a start, but sunlight-powered rovers would struggle in the shadows. The terrain is treacherous, communication is tricky, and the cold would kill most electronics in minutes. Still, the promise was too great to ignore. These strange craters had become the hottest cold targets in space exploration, drawing missions from around the world. The mystery deepened. Were the PSRs truly hiding ancient ice, or were they just barren bowls of rock? To find out, the next step was clear. We had to start looking for real, measurable signals that could settle the debate. From whispers to impact, the story of lunar water didn't begin with drama. There were no glittering ice sheets spotted from space and frost shimmering in photographs. Instead, it began almost quietly, buried in the back pages of scientific reports and lab notebooks. In the 1970s, while the Apollo program was winding down, another player stepped onto the stage: the Soviet Union's Luna 24 mission. Luna 24 was far from a headline grabber. It didn't carry astronauts, and it didn't broadcast images of men bounding across the lunar surface. It was a robotic probe with a single job: drill into the soil and bring a sample back. Its core was only about 6.5 feet long, weighing less than half a pound. But inside that slim column of dust was something unexpected: faint traces of water. The concentration wasn't high, about 0.1%, but the pattern was striking. The deeper the sample went, the more water appeared. To a few researchers, it hinted at a hidden reservoir beneath the gray regolith. Yet the response was swift and dismissive. Surely the signals were contaminated, moisture from Earth's atmosphere sneaking into the samples after arrival, or residue from the spacecraft itself. The explanation was comforting because it meant nothing in the textbooks needed to change. The moon, officially, remained dry. The same fate had already befallen the Apollo samples. When American scientists found trace hydrogen-bearing compounds, possibly hydroxyl or water molecules, they too were waved off as artifacts. In the cautious world of science, it was safer to assume error than to challenge decades of certainty. And so, for nearly 25 years, the hints of lunar water were archived and ignored. By the late 1990s, however, the picture began to shift. New technology, sharper instruments, and a willingness to re-examine the past reopened the case. Remote sensing data suggested that hydrogen was lurking at the poles, particularly in permanently shadowed regions. In 1994, Clementine mapped the polar terrain and flagged craters in permanent darkness, credible cold trap candidates, even if it couldn't see what was inside. Then, in 1998, Lunar Prospector used neutron spectroscopy, tracking how particles scatter from the surface, to pinpoint hydrogen enrichments at both poles. On paper, that implied on the order of 10 to 300 million metric tons of potential ice, attention-grabbing even with big uncertainties. Still, hydrogen alone isn't proof of ice. It can reside in hydroxyl or be bound within minerals, so orbiters could hint, not certify. But suspicion and hints weren't enough. To prove the case, scientists needed direct, undeniable evidence. And to get it, they turned to an unusual strategy: brute force. Early impact attempts tried to force the issue, Lunar Prospector in 1999 and Kaguya in 2009, yet both produced dust and ambiguity, with no water detection to show for it. The idea was simple. If ice really was hidden in a shadowed crater, and if orbiters couldn't confirm it from afar, then maybe smashing something into the moon would toss material into the sunlight where it could be measured. It wasn't subtle, but it promised clarity. That bold approach came in 2009 with NASA's L-CROSS mission, the Lunar Crater Observation and Sensing Satellite. L-CROSS didn't travel alone. It carried with it the empty upper stage of its launch rocket, a massive piece of metal that would serve as the first impactor. The target was Cabeus Crater near the South Pole, chosen because of its permanent darkness and its potential to act as a cold trap. The sequence was almost theatrical. First, the rocket body slammed into the crater at high speed, blasting a plume of material upward. Minutes later, L-CROSS itself dove straight through the rising cloud, instruments primed to sniff out whatever was hiding in the debris before it too met its end on the crater floor. The gamble paid off. L-CROSS detected clear signatures of water vapor. Alongside it came other volatile compounds: carbon monoxide, methane, ammonia. For the first time, lunar water wasn't a laboratory curiosity or an orbital suspicion. It had been measured directly, in the very act of impact. The result made headlines around the world. The moon, once thought to be completely dry, had just confirmed the presence of water. To the public, it sounded like a solved mystery. But to scientists, the finding raised new layers of questions. L-CROSS had shown what was present in one crater, in one place, at one moment in time. But was Cabeus unique, or just one example of a larger pattern? Was the water concentrated in discrete patches, or spread out in a thin layer across the poles? And perhaps most importantly, was it accessible enough to be useful? L-CROSS couldn't answer those questions because the mission had ended in destruction by design. Its role was confirmation, not exploration. But in doing so, it accomplished something profound. It transformed lunar water from rumor to reality. From the whispers in Apollo's labs to the roar of an engineered impact, the moon's secrets were no longer speculation. They were measurable. They were real. And with that confirmation, the stakes changed. The moon was no longer just an object of scientific curiosity. It was beginning to look like a resource, a place with the potential to support human life and missions beyond Earth. The whispers had finally turned into a shout, and the search for water was about to take a far stranger turn than anyone expected. The moon that sweats. The L-CROSS impact had proven that water was hiding in the shadows, but the story didn't end there. In fact, just as scientists were celebrating that confirmation, another surprise emerged, one that complicated everything we thought we knew. Because water wasn't only lurking in dark craters. Against all expectations, faint traces were showing up out in the open on the sunlit surface of the moon itself. This puzzle came into focus thanks to two missions working in tandem: NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1. While both were designed primarily for mapping and mineral studies, their instruments were sensitive enough to detect chemical fingerprints on the regolith. And what they found was astonishing. Across wide stretches of lunar terrain, signatures of hydroxyl and water molecules appeared, scattered, thin, and fragile, but present nonetheless. Even stranger was how those signals behaved over time. During the lunar day, especially around midday when the surface temperature soared above 250 degrees Fahrenheit, the water signatures weakened or disappeared entirely. But as the surface cooled in the evening, the signals returned. It was as though the moon itself was exhaling and inhaling, losing water molecules in the heat and regaining them as the temperature dropped. This wasn't water in any familiar form. No puddles, no frost sheets. These were just molecules clinging to the surface or migrating through the moon's paper-thin exosphere. But their presence revealed something new, a dynamic cycle. The moon, once thought inert, seemed to sweat at a molecular scale. Theories emerged to explain it. One possibility was that micrometeorites, constantly peppering the surface, were delivering water molecules or liberating them from minerals on impact. Another involved the solar wind. The sun bombards the moon with streams of charged hydrogen particles. When those particles strike oxygen-bearing minerals in the regolith, they could create hydroxyl groups, and over time, some of those could combine into actual water molecules. Chandrayaan-3 and the patchwork problem. The confirmations from orbiters and the L-cross impact had given scientists confidence that the moon wasn't dry after all. Hydrogen signals glowed in maps of the poles. Volatile compounds had been measured in the plume of a shadowed crater. Everything pointed to a simple conclusion. Water was waiting to be found on the ground. All that was needed was a lander to put the question to rest. In 2023, India attempted exactly that with Chandrayaan-3. Unlike earlier missions that orbited from afar or crashed into the surface, this spacecraft was designed to land, survive, and measure in detail. The target was the South Pole, the region most likely to contain ice according to years of orbital data. If hydrogen were abundant anywhere, this was the place. The Vikram lander touched down successfully, making India the fourth nation to achieve a lunar landing and the first to operate near the South Pole. Rolling down a ramp was Pragyan, a small rover carrying instruments capable of probing the chemistry of the regolith directly. Its tools included a laser-induced spectrometer and an alpha particle X-ray spectrometer, both capable of identifying the elements in the soil with precision. The mission had one major expectation: to detect hydrogen. Orbital maps had practically lit up with its signature in this region. And since L-Cross had already confirmed water vapor from an impact at another polar crater, Pragyan's task seemed straightforward. But when the rover began firing its lasers and analyzing the returned light, the results didn't line up with expectations. Instead of hydrogen, the rover detected a range of metals: aluminum, iron, calcium, chromium, sulfur, even titanium. Each element told a story about the moon's geology, but the crucial signal scientists were waiting for was missing. No hydrogen, no confirmation of ice. The most promising region on the moon had returned a puzzling result: dry soil, at least at the surface. At first glance, the findings were discouraging. How could so many years of orbital data point to hydrogen if it wasn't present on the ground? Had scientists misread the signals? Or was the water real but hidden from the rover's reach? Vikram's other experiment offered a clue. Its CHAST probe recorded approximately 140 degrees Fahrenheit at the surface and approximately 14 degrees Fahrenheit just 3 inches down, a steep drop that screams insulation. That sharp gradient showed that the regolith acts as a thermal blanket, keeping shallow layers far cooler than the surface above. This property means that while the surface bakes under sunlight, the material just below can stay much colder, and if ice does exist, it could be hiding just beyond the shallow reach of Pragyan's tools. From orbit, broad signals of hydrogen could still appear strong because satellites detect integrated signatures over depth and distance. But a lander probing only a few inches might miss it entirely. This wasn't just about one mission coming up dry. It highlighted the fundamental difficulty of lunar exploration. Different tools see different things. Orbiters scan wide areas from hundreds of miles up, but they can't distinguish whether hydrogen is in thick deposits or thin films. Landers measure with certainty, but only at the precise spots where they happen to touch down. Impact experiments confirm volatiles, but only in a single plume. Taken together, the results painted a new picture. Lunar water isn't a uniform reservoir waiting to be tapped. It's patchy, varied, and exists in multiple forms. Some of it may be grains of ice trapped in permanently shadowed soil. Some may be thin films that cling to dust particles on sunlit ground. Some may be hydroxyl groups bound inside minerals, locked away in crystal structures. And still more may exist in micro-cold traps, tiny patches of shadow only a few feet wide, cold enough to preserve ice for eternity. Each of these forms behaves differently, and each requires different instruments to detect. That's why Chandrayaan-3 and the orbiters didn't agree. Both were right. They were simply observing different slices of a far more complicated system. This realization shifted the scientific question yet again. It was no longer simply, is there water on the moon? The answer to that was now yes. The real challenge became, how much of it is there? Where exactly is it? And can we ever use it? Chandrayaan-3's puzzling results weren't a failure. They were a turning point. They showed that the moon isn't hiding a single secret, but a patchwork of them. Each crater, each region, and perhaps each grain of dust could hold a different answer. And finding those answers will require not just sharper tools, but a new way of thinking about what the word water even means on the moon. The warped interior. While much of the attention has focused on the moon's surface and its hidden water, another set of discoveries has revealed something even stranger. Beneath the gray dust and craters lies a world that isn't balanced or uniform at all. The moon's interior is lopsided, almost warped from within, and in at least one region it hides an enormous metallic mass left over from a cataclysm that reshaped its history. The evidence for this began with NASA's Grail mission, the Gravity Recovery and Interior Laboratory. Launched in 2011, Grail consisted of 2 spacecraft flying in tandem, mapping the moon's gravity field with remarkable precision. By tracking the tiny changes in their speed and distance as they orbited, scientists could see where gravity was stronger or weaker. These variations revealed not only surface features, but also what was happening deep inside. What they found was unexpected. The side of the moon that always faces Earth flexes far more than the far side under our planet's pull. This tidal flexing is measured using something called the love number, a value that describes how much a body deforms under gravity. For the moon, the near side's value was shockingly high, 72% greater than models predicted. That result forced researchers to confront a new reality. The moon wasn't symmetrical inside. The explanation lies in heat. Billions of years ago, when the moon's crust was still forming, radioactive elements like thorium and uranium didn't spread evenly. Instead, they concentrated on the near side, the face that always looks toward Earth. As those elements decayed, they released energy, keeping the mantle below warmer and less rigid than the far side. Over time, this imbalance fueled massive volcanic eruptions that resurfaced the near side with dark basalt plains, called Maria, while the far side remained rugged and ancient. This thermal asymmetry explains why the two hemispheres look so different, but it also means the moon's interior has been evolving unevenly for billions of years. It's not just a cosmetic difference, it's structural, written into the very bones of the moon. But Grail revealed more than just a lopsided interior. When scientists turned their attention to the South Pole Aitken Basin, one of the largest impact craters in the solar system, they discovered something even more bizarre. Beneath this colossal scar, which stretches about 1,600 miles across and more than 8 miles deep, lurks a dense mass of material pressing downward with immense force. Its size is staggering, roughly 5 times larger than the big island of Hawaii, and it distorts the moon's gravity field so much that orbiting spacecraft can feel its tug. The leading theory is that billions of years ago, a giant asteroid with a metallic core slammed into the moon. Instead of vaporizing completely, part of that dense core became embedded in the lunar mantle, where it remains buried today. In effect, the moon swallowed an asteroid and never digested it. This buried heavyweight explains the gravitational anomaly and offers a rare window into the violent history of planetary impacts. The presence of this metallic mass isn't just a curiosity. It could have influenced how the crust fractured, how volcanic activity unfolded, and even how volatiles like water migrated through the region. And it's located right in the neighborhood where modern missions are aiming to search for ice. That means the very area scientists see as most promising for resources is also shaped by one of the most disruptive features on the moon. Taken together, these discoveries show that the moon isn't a simple sphere of rock. It's geologically asymmetric, with one side warmer and more active than the other. It carries the buried core of an ancient impactor that still warps its gravity. And those internal oddities aren't just academic. They shape the surface conditions, the stability of potential ice deposits, and the challenges of exploration. What's most striking is how long these secrets remained hidden. For centuries, the moon was seen as a steady, unchanging companion in the night sky. Even after astronauts walked its surface, we thought we understood it as a dead world, frozen in time. Yet gravity measurements and orbital maps have revealed that beneath its calm exterior lies a story of imbalance, violence, and survival. Unlocking the lunar future. The moon has revealed itself to be far stranger than the simple world many once imagined. From hidden ice that comes and goes with the sun, to interior lopsidedness, to a buried mass of metal warping its gravity, each discovery has challenged old assumptions. But despite decades of missions, the truth remains incomplete. The only way forward now is to stop circling questions and start pulling answers from beneath the surface. That means drilling deeper, surviving longer, and proving whether the moon's hidden resources can really sustain us. The first step is hardware. Landers and rovers so far have only scratched the skin of the regolith, reaching inches when they needed to reach feet. Future probes will need stronger drills capable of extracting cores while preserving fragile volatiles like water ice. Downhole neutron detectors, ground-penetrating radar, and thermal probes must work together, layering data until the mystery of what lies beneath is finally settled. Instruments like ShadowCam are already proving their worth by peering into craters darker than midnight, but they too need partners on the ground. Even so, no bright mirror-like ice sheets have yet been spotted in those shadows, a reminder that the moon continues to guard its secrets closely. Then comes survival. Missions to the polar regions must endure the brutal lunar night, a 2-week stretch of darkness when temperatures plunge far below -250 degrees Fahrenheit. Solar panels alone can't carry a rover through that kind of cold. Nuclear-powered heaters, compact reactors, or radioisotope systems will be required if explorers hope to last long enough to gather the evidence. And for human missions, durability will matter even more. But the prize makes the effort worth it. If lunar water can be confirmed in usable amounts, it transforms the moon from a destination into infrastructure. Ice can be purified for drinking and life support. It can be split into hydrogen and oxygen, producing rocket fuel far cheaper than launching it from Earth. With gravity at about 1/6 of Earth's, launching that propellant from the lunar surface changes the economics of spaceflight entirely. What was once a desolate satellite could become the gas station of the solar system. Yet honesty demands caution. So far, the moon has defied easy answers. Hydrogen signals that glow from orbit fade at the surface. Impact plumes confirm water in one crater while others appear bone dry. The interior flexes unevenly, reshaping theories of its history. Even the technology we use has failed us, with multiple landers in recent years crashing after faulty altitude readings. None of it has been simple. but exploration rarely is. The moon's weirdness is not an obstacle, it's an invitation. The next drill, the next lander, or the next astronaut may finally uncover what centuries of speculation could not. And when that moment comes, the moon won't just be Earth's companion in the night sky, it will be the first stepping stone toward humanity's permanent place among the stars. Thanks for watching to the end. Which part stood out to you the most? Drop your thoughts in the comments. We always enjoy reading them. If you liked this deep dive, hit that like button and subscribe for more. Let's keep chasing the mysteries of the universe together. Until next time, stay curious and take care.